Okay, so here we go. Let's go ahead and start with Unit 3. So we're actually going to finish up Chapter 21 in this lesson, and then we'll just get barely started in Chapter 22. That is the plan. All right. So with regards to Chapter 21, the one type of functional group that we haven't discussed yet are the amides. Now we know some things about amides. We really have gone over most of this in previous chapters, but this is the lesson where we really focus on the amides. So one reason why they are important is because they are all over the place in living organisms, okay? The amino acids that make up proteins, those form amide linkages, okay? We call those peptide bonds, right? But they're also formed in nucleic acids, okay? And in a lot of other pharmaceuticals, as you can see in the diagrams there, okay? So protein, something like a penicillin derivative, and then in the nucleic acids, the connection between the ribose and the base itself is an amide functional group, okay? Part of the reason for that, we see them a lot in nature, is because they're so stable, right? It's kind of like a plateau, if you will, of stability. Among the carboxylic acids, the amides are the least reactive. They are the most stable. Okay, the typical way to prepare them is to first prepare the acid chloride, which is the most reactive carboxylic acid derivative. And then you just react that with either ammonia, if you want an unsubstituted amide, or if you want a substituent or two on that nitrogen, then you just react it with a substituted amine, okay? And that will result in the different kinds of amides, whether you have just an unsubstituted amide, as you see there on the right, both hydrogens are still on the nitrogen. Or if you start with a primary amine, you end up with what's called a secondary amide, because now the nitrogen has two non-hydrogen substituents on it, right? This would be a secondary amide. Or if you react that acid chloride with a di-substituted amine, okay, so a secondary amine, then you end up with a tertiary amide, because now this nitrogen, it's substituted in three positions with R groups, okay, and it does not have any hydrogens on it, so that would be a tertiary amide. So the terminology shifts when you're talking about the amine versus the amides. So just be aware of that, because that acyl group, that carbonyl group, that counts as a substituent on the nitrogen. So the terminology kind of shifts in that regard. Okay. So since they are the most stable, we would suspect that it's hard to convert it into something else, and it is, but you can. And so it can revert back to a carboxylic acid through the process of hydrolysis. But typically what you have to do is you have to heat it. You have to supply that additional energy to get it over the hump. So you heat it in either aqueous acid or aqueous base. And as you said, this is hydrolysis, so it reverts back to a carboxylic acid and an amine. Those are like the starting materials that make the amide in the first place, used to prepare the amide. So if you revert back, then you're going to get the carboxylic acid and the amine back. Okay, so here's an example. Here's an example of the acid catalyzed, right? That's what this means. And so as is the case in many instances where acid is the catalyst, what it does is it protonates the oxygen on the carbonyl, which activates the carbon, making it more electrophilic. So now a water molecule can act as a nucleophile and attack that carbonyl. Okay, so there's your water molecule that was added. So you get the tetrahedral intermediate. Okay, and now if you think about it, the only thing that can serve as the leaving group in this situation and lead to something else, to a new product, is if that amine now leaves. Okay, but in order for that to happen, it has to get activated as well. So, one of the hydrogens on this water that was just added, this is the water molecule that was just added. So it transfers a hydrogen over to the amine, and that's kind of implied. It doesn't directly show that in this reaction mechanism with curved arrows, but that does happen. And so now that NH2 becomes an NH3+. And so now it's a good leaving group because it's got that positive charge and it would result in a stable, leaving group. And you get the carboxylic acid back. But again, because this is a weak base, it's probably going to react with your acid catalyst. You regenerated the catalyst, the acid catalyst, and it's going to just generate that NH4, okay, the ammonium ion, because it in itself is a weak base. Okay, so this is just the mechanism of the hydrolysis of an amide when it's acid catalyzed. It's a little simpler when you do it with a base, because remember that the hydroxide is going to be a stronger nucleophile than water. So it just attacks the carbonyl. You don't need to activate the carbonyl. It's just a strong enough nucleophile to attack the carbonyl. Again, you get that tetrahedral intermediate. And once again, the only thing that can leave in order for you to get a different molecule to cause a transformation, the only thing that would leave is that amide ion, okay? So that's odd because, that's typically not a good leaving group, and it's not, but it's not going to stay that way for very long. So once that NH2 minus leaves, it reacts with the carboxylic acid to abstract a hydrogen, it's acid-base reaction, to give you the carboxylate and then an ammonia. So that's the only thing that really facilitates this, is that the leaving group, once it leaves, can then react as a base and it becomes more stable. So that sort of facilitates that process. And then if you wanted to actually get the carboxylic acid, you would have to do another step where you treat this carboxylate with a strong acid to protonate it. Okay, so once again, this is, it's weird because you've got this amide ion or amide ion. Again, I'm not sure how it's pronounced. When it's an organic functional group, as I said before, I call it amide. But for whatever reason, I have always called it, when it's an ion like this, NH2 with a negative charge, I always call that an amide, kind of like chloride or fluoride. Those are negatively charged ions. I think I just got into that habit. But that's the key, is that's a really bad leaving group, but it's okay because it doesn't stay that way for very long. It just grabs that hydrogen and becomes a stable ammonia. All right. Now, that's one transformation that we want to talk about. The other one that we've commonly talked about with these carboxylic acid derivative functional groups is the reduction of them. So amides can undergo a similar kind of reduction. The typical reducing agent is the lithium aluminum hydride, once again, because it's the one that's strong enough. The sodium borohydride, NaBH4, is just not strong enough. And same thing happens that it's happened with every other carboxylic acid derivative. What you're doing is you're adding hydride to the carbonyl, carbon, forming a CH2 group. So you're transforming the C double bond O into a CH2. Okay, and the hydrogens are coming from that lithium aluminum hydride. And then the byproduct then really is water. It happens twice, and so the oxygen from the carbonyl leaves, and it leaves with hydrogens from the water, forming a water molecule, and you just reduce that down. Okay, and this is one mechanism I don't expect you to know, so you just need to, well, you do need to know where the source of the hydride is. The hydride comes from the lithium aluminum hydride. But the step-by-step mechanism you don't need to know. Okay? Oh, no, actually I have to contradict myself. So this one doesn't form water as a byproduct. What it does is the oxygen gets attached to that lithium. Okay, or pardon me, the aluminum. I'll get it right. So the oxygen ultimately gets attached to the aluminum from the lithium aluminum hydride. Okay, so you see that here in this reaction. So the hydride from the lithium aluminum hydride attacks the carbon. The electrons move up onto the oxygen, make that an alkoxide, but then that attaches to the aluminum, the AlH3. Okay. And then you have this iminium ion intermediate. Okay. So this is a pretty good route for forming a cyclic amine, and you'll see we have an example of this, but it's easier to form first the cyclic amide, lactam, that's the name for that, lactam, and then just reduce that lactam down to an amine, and then you get a cyclic amine. So this is a good way to prepare a cyclic amine from a lactam. So you can see that in this example. So you start with your lactam. Remember, that's just the special name we give to a cyclic amide. Okay, and then we just react that with the lithium aluminum hydride. Add hydrogens there. And so now, bada bing, bada boom, you got your cyclic amine. Okay? All right, so let's do a little practice on this one. So again, just take a look at your handout there. I'll give you a minute. I'll freeze the screen. See if you can come up with a scheme to convert this into benzoic acid. Okay, so think about that. Oh, I forgot mine. I forgot my pad. So I don't even know if I can. Nope. Okay, so let me just go ahead and I did forget my writing pad. I apologize, but we'll keep going. I don't think it's worth my time to go downstairs and get it. But the big thing is just, you know, the way that you revert it back to the carboxylic acid is you just heat it up with acid or base. It's typically acid. You'll see as we get further into this unit that, you know, acid hydrolysis is typically what's done. Okay. But recognize that what you've split off is, you know, you added that OH2 here, but you split off this, and so this forms an amine. Okay, so you got the amine as a byproduct, and because that's a weak base, it's also just going to react with your acid to form an aminium ion, where it's got the positive charge on the nitrogen, just like an ammonium ion. But there you go. Okay. Okay, now this one, I am going to freeze the screen again. And so think about this one, and I'll actually do this one on the whiteboard because, you know, I think it is important to see some things here. But go ahead and freeze the screen. So think about this one. This will involve two steps. You can just kind of check your work as I write this out. Okay, so to make this transformation, you're going to need to do it over 2 steps. So as I said, this is a common way to make a cyclic amine. So you get, and I didn't even show this step, but probably what you would do is you would start with the carboxylic acid, and then you would convert that to the acid chloride with something like thionyl chloride, SOCl2. So, you know, we would have like the carboxylic acid, and then we would react that with SOCl to thionyl chloride to get the acid chloride. And I didn't show that there, but that's kind of implied, because there's no way you could even isolate this right here. Okay, but then what's going to happen is this nitrogen is going to act as a nucleophile, and it's going to react with this carbonyl. Okay, close up the ring. So that arrow that I drew, the curved arrow there, forms that bond between the nitrogen and the carbonyl. And what promotes this is pyridine. Now, typically, what you could do is you could just have 2 equivalents of the amine, but in this case, you know, all of them probably are going to react. So it's good maybe to have an external base there, like pyridine, to remember its role is just to sequester that hydrogen that pops off the nitrogen, right? And then the Cl from the acid chloride. So it forms that ammonium chloride type compound. Okay, so that gives you the ring. And then, as I said, you can reduce that carbonyl with step 2 by just adding the hydrides, the H-, they attack that carbonyl. And you do it twice. So times 2 maybe, you know, just have 2 equivalents of the lithium aluminum hydride. Okay. So actually, let me do one thing, just to make it even, if you're still wondering where things are, let's number things here. So let's say this is carbon 1, this is carbon 2, carbon 3, carbon 4, carbon 5. Okay, so that means this is 1, 2, 3, 4, 5. Okay, and then the nitrogen, Okay, and so here would be like carbon 1. It's kind of, you know, rotated a little bit. So carbon 1, 2, 3, 4, 5, if that helps. Okay. All right. Okay. So one of the things that we talked about in the last lesson, lesson 15 of unit 2, was polyesters. And that's where you take this compound that's got a functional group on each side of it, and you use that to make like links in a chain. Okay, well, you could do that with amines and acid chlorides as well. And instead of it being called a polyester, since you're forming amide bonds, amide functional group, we would call that a polyamide. Okay. Also, you know, well known as like nylon. That's the more common name. There's lots of different types of polyamides. As we mentioned earlier at the beginning of the lesson, a protein is a polyamide, really, because what connects each residue, each amino acid, is an amide functional group. So when you have the reaction of a diamine with a diacid chloride, you end up with a polyamide. Okay, and oh yeah, unfreeze the screen. Thank you. Thank you. Yep. And again, just to connect it to what we went over in the last lesson of Unit 2, it's very similar to what we described with the polyesters, just with an amide functional group instead of a ester functional group. Okay. All right. So that's pretty much it for chapter 21. Now we're going to launch into chapter 22, but not before reviewing a little bit about something that we've introduced already in this course, and that is the keto-enol tautomerism. Okay, so look at the figure here. There's basically these three pictures tell the story. Okay, so a tautomer is kind of like a resonance property, but it's not the same. With resonance, it's just where multiple bonds have moved around in the molecule and give you equivalent structures. Here, we actually have atoms moving. So it's color-coded here. This sort of brown hydrogen in the keto form, the ketone form, is on the carbon, but in the enol form, it's attached to the oxygen. So if you're pushing electrons, the electrons in this carbon-oxygen double bond move up onto the oxygen. This bond between the carbon and the hydrogen moves to become between the oxygen and the hydrogen. Okay, and then well, I should say the electrons themselves go into making this double bond between the two carbons. That's where you get the ene part of it, and then the ol part of it comes from the fact that you got the alcohol. Remember that ol is the suffix for an alcohol. So ene for the double bond and ol for the alcohol functional group. But if that just rearranges, where you reform, it's a reversible reaction. So if it reforms the carbonyl, then what you have is a ketone. Okay, so we call that an enol. Okay, and this always exists. It's just degrees of and proportions. So in a compound like cyclohexanone, well, that's where 99.999% of it looks like that. Okay, but a small amount of it, in this case, 0.0001% of it, is in the enol form. And that just depends on the structure of the ketone / enol. All right. Now, the other property that is important to remember about this type of compound is that because of that, these alpha, the hydrogen's on the alpha carbon. So again, the terminology is important. So the alpha carbon is the carbon that's right next to the carbonyl. So here's your carbonyl. So the carbon adjacent to that is the alpha carbon. And those hydrogens that are attached to that carbon are what we would call relatively acidic. They're not strongly acidic, but it doesn't take a whole lot of effort to rip those off. And again, that's because of the resonance that exists with the anion that's formed, the carbanion. So if we rip off one of those hydrogens, it dumps its electrons onto the carbon to give us the carbanion. But that is stabilized by resonance because it can form that double bond between the two carbons, and it pushes the electrons up onto the oxygen. And so now the oxygen houses that formal negative charge. And oxygen's an electronegative atom, so it doesn't mind that so much. So these are two resonance forms that stabilize that negative charge. And so that makes those hydrogens slightly more acidic than just a normal carbon-hydrogen bond. Okay, so we just needed to review that a little bit before we move on to the next topic. Okay, and the thing is, you can catalyze this transformation between the two forms either with an acid or with a base. So for example, if I have it under acidic conditions, what you do, as again is so often the case, you start the process, you kickstart the process by protonating that oxygen that's in the carbonyl. So it grabs a hydrogen from a strong acid, okay, forming that protonated carbonyl, which has the formal positive charge in the oxygen, but it can resolve that by just, moving a pair of electrons off that carbon, okay, onto the oxygen. So it moves a pair of electrons from the CO double bond onto the oxygen. And that gives a formal positive charge to the carbon. But then a base, this, let's just say whatever the conjugate base from the original acid can come along and take a hydrogen from that adjacent carbon, and then it pushes its electrons into the carbon-carbon bond to make it a double bond, and that fixes the formal positive charge on the carbon. See that it's gone, you got the double bond. And so, in a sense, you regenerate the catalyst. So, and you get the enol tautomer versus the keto tautomer. So that's with acid catalyst, but you could do the same thing with a base, but the base just operates by a different mechanism. So the base, something like a hydroxide ion, can just rip off one of those alpha hydrogens. And that gives us the carbanion, right? Because it dumps its electrons onto the carbon, making it a carbanion. Okay, well, then the double bond between the carbon and the oxygen in the carbonyl move up onto the oxygen. Those electrons move between the two carbons to make the carbon-carbon double bond. And so then, this is probably, an aqueous solution. So if we could regenerate the catalyst and protonate that oxygen in another step with a water molecule, so that oxygen that's negatively charged now takes a hydrogen from a water molecule to regenerate the catalyst, and it gives us the enol form. So again, we start with the ketone form, we have the enol form. It's just catalyzed by either acidic conditions or basic conditions. Okay, so again, we're really just reviewing things, but it's good. Okay, so what we really focus on in the next chapter is this substitution reaction that's facilitated by this property, this keto-enol tautomerism. So one of those hydrogens that's slightly acidic can be replaced with just a different electrophile. H+ is an electrophile. So we could exploit this keto-enol tautomerism to just replace that with a different electrophile. So we could do a carbonyl alpha substitution. So what was a hydrogen that was alpha to a carbonyl can just get substituted with another electrophile. So a hydrogen atom on the carbon adjacent to a carbonyl group is replaced by another atom or group acting as an electrophile. So, okay, so you can see that here just with E representing an electrophile. Okay. And then if you look on the back there, it just has the mechanism sort of when it's acid catalyzed. We don't have the mechanism laid out when it's base, when it's catalyzed by a base. But so if we have an acid, we protonate the the oxygen here, okay, and then that gives us, it gives us the enol form, okay, and then we create this electron-rich area with the carbon-carbon double bond that acts as a nucleophile towards some other electrophile. And in the future lessons, we'll talk about what those electrophiles might be. So then it just forms an electrophile, and then you just regenerate the ketone form, but instead of a hydrogen, you have the other electrophile attached now, okay? All right, so that's it. So let me go ahead and stop the share in this. And I think I will, let's